Okay, good morning, everyone. Massive welcome to those that have been able to join us live. That's brilliant. And for anyone who has registered but watching this back as a recording, welcome to you as well, whenever that date may be. So you're all joining us to listen to our presentation on linking between elemental analysis and molecular analysis for agriculture, agri-food, and feeds. And hopefully you'll find this session educational. It's going to be hosted by myself, Tom Knott, who's one of the product managers here at SciMed, and Darren Machin, who you'll visit shortly, whose camera has just popped on. Hi, Darren.
Good morning.
The structure we plan will be as follows. After this brief introduction, I will begin by giving everyone here an overview of the elemental analysis approach, primarily with a focus on EDXRF, which is emerging as a useful tool in this sector and also as a useful alternative or complement to other conventional elemental analysis tools that some of you may be familiar with. Of course, with any technique, it comes with many advantages and also disadvantages to consider. And that's where we see a nice synergy with the molecular analysis. So I will then pass over to Darren, who can walk you through the applications and tools that we recommend and utilize for that kind of work. Throughout the presentations, there will be a live Q&A active. You will see that towards the top of your screen marked as Q&A. At any time, feel free to type or pop a comment in there if you have a question. We will deal with all questions at the end of the webinar, but please put them in throughout that as they pop up. If you're anything like me, if you don't ask it when it crops up into your head, it'll be forgotten by the time we get to the end. So we'll deal with as many as possible, and then we'll close out. And as I've already mentioned, following the session, we will ensure that a recording is sent over to all those that have attended and registered for future watching and consideration. So let's move on from there. So as I mentioned, I will open with elemental analysis. I am the XRF product manager here at SciMed. SciMed are a 45-year-old company described as the leading supplier of scientific equipment in the UK. We're a distributor, but we're very proud of that with our tagline of global brands representing the many suppliers and different techniques across our wide portfolio. But most importantly is the local support. So people like myself, Darren, and our extensive team are all coming from a variety of industrial or academic and scientific backgrounds. So we really take a level of pride in discussing various applications with end users in order to try and recommend and discover the best solution together. So without further ado, let me give you an overview of what I believe XRF can support across your industries. And again, as always, I'm going to welcome any questions as we go through. So when we mention XRF, for those that may not be familiar intimately with the technique, we're talking about the interaction of incident X-rays with matter, and in this case, it's related to foods and animal feed, and causing an interaction in the atomic structure, primarily the ejection of an inner orbital electron, which then leaves the individual atoms of the sample temporarily unstable, and outer orbital electrons cascade down to fill those vacancies, and in doing so, release secondary X-rays that are characteristic of the individual elements producing them, and thereby by counting them through the counting electronics of various systems, we can approach quantification of the elemental makeup of those samples in various forms, be that solids, powders, pellets, liquids. XRF is very forgiving in the sample form, and we'll touch on that a little bit later. But most importantly, it's non-destructive and requires very little sample preparation in comparison to other techniques that may be utilized. You can split EDXRF, which stands for energy dispersive, i.e. you're distinguishing the different characteristic X-rays based on their characteristic energies, and you can split it into two families from the instrumentation point of view. You either have those that are direct excitation, whereby it's a very simple geometry of X-rays in, excitation of the sample, X-rays out straight to the detector with no other pathways or interactions going on in between. What is perhaps becoming more popular in more modern systems is indirect excitation, whereby the incident X-ray beam is first passed through a secondary target and thereby polarizing the energy of that incident beam. And in doing so, it very much drops down the background noise that can be a characteristic of direct excitation systems, cleaning up the signal, meaning that XRF can attain vastly improved detection limits compared to conventional understanding. As I mentioned earlier, we represent many global brands, and for XRF, we're proud of our partnership with Rigaku that have a very wide range of benchtop energy dispersive systems that fit across that family of instrument approaches that I've just outlined. And having that available to us means that we're never short of being able to recommend a solution that's best suited for both funding, performance, lab space, which we all know in the UK is always at a premium, and the wide range we've got across that means there's always something worth discussing. But I promise that will be the last piece of direct sales you'll hear from me this morning. So when we look at agriculture and the subject of agri-food in general, I wanted to throw up this kind of flow chart because it's useful to look at, as XRF elemental analysis can feed in to pretty much everything across this flow chart, starting from the soils, the crops, and how they feed into the animal feed and ultimately to food to us. There's a way that we can take part in all part of this flow chart, and I wanted to cherry pick out a few areas of this to show examples of what it is I'm trying to address. So starting first with soils. For those of us that work with soils, I have a geological background myself, so I did quite a lot of soil analysis for kind of structural controls. But even when you're looking at agriculture, the soil is where the story begins. You know, if you don't have the right mixture of nutrients and components for both structural properties and nutritional properties as well as the soil, then your crops are not going to perform very, very well. And where XRF can lend itself to this is in giving you that way of being able to monitor elements right the way from sodium all the way up to uranium in staggering cases, but importantly on a wide range. So detection limits for XRF, certainly in organic matrices for things like soils, ranges from single-digit parts per million at the lower end to maybe thousands of ppm on the lightest of elements, but right the way up to tens and right up to 100%. So very forgiving, got a wide range of compositions, but you can also measure all elements simultaneously. So everything from the lightest to the heavy metals we want to closely monitor, you're getting signals from all that at the same time in a single instrument and a single analysis. As I said, why might that be important? Well, when we consider the study of agronomy, the soil, as I've already highlighted, is the first point of call for that as to how foods, feeds, and primarily the plant matter is going to develop, grow, and take up. But also the XRF doesn't just start and stop at the soils. You can also take samples of the dried plant matter, or even wet plant matter for that matter, though dried just helps the sample form a little, compress that into a little cup and measure it directly and get that deeper understanding of what was my elemental understanding of the soil versus what's the uptake into the plant. And in doing so, approach soil conditioning, and in other interesting areas, plant breeding as well can help selective breeding in terms of the uptake of certain nutrients, certain elements. You can gear it in all these sorts of ways by having on-site instant monitoring of the elemental composition of both the soil and ultimately to the plant. That, of course, is undoubtedly going to have a knock-on effect onto things like animal feed. So for those of you that are intimately working with animal feed, you will know the range of nutrients and also heavy metals and things you need to monitor either in your premixes and in your final feeds. And many of the raw materials from that have come from soils, direct mineral things like limestones, and maybe even plant matter as well, all of which you could have monitored at every stage in order to fill in the full picture when it comes to the development and the formulation of various pet foods and animal foods, be they wet or dry. And it doesn't have to be the final feeds that people like yourselves are working with. It can be in, as I've already highlighted, the plant matter and foods that you're feeding the very animals that are ultimately going to need to be monitored for both the nutritional benefits and healthcare of the animals themselves, but also how that's going to impact food and human consumption down the line. So it's becoming a increasingly common request I get for, can we simultaneously monitor our feed products but also receive and analyze things like fodder and silages and haylage for their elemental composition. And as long as the sample is prepped in the correct way into simple sample cups, which I'll cover shortly, the answer is yes. You get a wide range of elemental information on those sorts of samples. And as much as I would love to go into many of these in detail, and as I say, if anyone has questions or things they want to pick on this during this session or afterwards, I'd be happy to provide further information. But it doesn't stop with just those first few examples I highlighted. As I said, the entire flowchart of the agri-food industry can be contributed to with elemental analysis via XRF, be that the fertilizers and the kind of looking at the circular economy and the more environmental approaches to fertilizer and waste reusage for that purposes, but also monitoring the final feed products for things like our consumption or for our children's consumption, like my young children with formulations. Those numbers on the back of the nutrient loadings for various elements like iron and zinc no longer became just a number. They became an understanding of how carefully and diligently that had been monitored. But it's important for me to highlight that XRF is becoming a bit of an emerging tool to be used in these industries. I'll be very happy to hear if any of you are already using it, because conventionally, many labs that you may send samples to externally or have in-house will use techniques such as ICP or AAS, atomic absorption, for their elemental analysis. And there are reasons behind that, of course, because the sensitivity and detection limits in terms of getting sub parts per million down to parts per billion, parts per trillion is achievable with these tools, but not achievable by XRF. But when some elements and minerals are there in percentage or tens, hundreds, thousands of ppm, you can potentially make your lives a little easier by not having to engage in the more in-depth sample prep and consumable costs of these techniques. But that's by no means to poo-poo this as a technique. And if you'll forgive me a shameless plug, that we also have a webinar on the calibration approaches and tools and considerations you can take from these techniques from our supplier analytic Jena and some of my other colleagues sometime in May. So do keep an eye out for that. And as I've just highlighted, I had to put this slide in as a bit of a disclaimer, because there's certainly colleagues in my organization that will be very upset to hear me saying up with XRF, down with ICP. It's certainly not the message. If anything, what this webinar will highlight between myself and Darren and in general is that collaboration and complementary support different techniques offer. And it's highly unlikely you're going to find a singular magic bullet technique to answer all your questions. And thereby, yes, you might get around some of the disadvantages with consumables and sample prep with ICP by screening with the XRF, but tools like ICP are not going to be replaced by another method. So to highlight some of those advantages, as I've just said, the benefits you do get from XRF, and a reason we're seeing a number of customers migrating to at least have one XRF tool, if not several, as part of their entire lab suite, is because you are mitigating the need for the aggressive chemicals or acids as part of the digestion process for some of these samples. If you're not desiring those super low level detection on certain elements, you can save a lot of time and by extension throughput and potentially cost in not having to go through that level of complex sample preparation. And by extension, you're going to get faster turnaround time because you can just put an aliquot of soil or a cluster of feed pellets straight over the analyzer. And within a matter of seconds to minutes, you're going to have a full, complete elemental analysis understanding in parts per million to percent of what that sample is made up of. And in doing so, it makes it much more user-friendly for kind of that more rapid look-see analysis that may inform part of the process. But as I've just said, there's never, ever a silver bullet in any technique that you're going to highlight. So it would be remiss of me not to highlight that the limitations are primarily it's around those detection. So you will all be more familiar perhaps than I am in terms of the increasing changes or developments in regulations demanding lower and lower, particularly for heavy metals, things like cadmium, mercury, for example. The reliable quantification limit in XRF is going to be around 1 ppm for those elements. If the regulations dictate you need to be a lot lower than that, then you're going to have that ability to move to another technique to further supplement the data you'd receive from XRF be that ICP or dedicated mercury analyzers. It's complementing those tools. And again, unlike methods like ICP, though I believe this is slowly but surely starting to change, is at present of recording this, there are no international standard methods that describe the approach for XRF specifically as a method, that they are those for techniques such as ICP. Now, the results from XRF are being shown as being highly correlated and aligned with those techniques. But for those needing to comply with standard test methods, it's important for me to highlight that those don't currently yet exist. And also the need with any technique, if you're not digesting things to remove those matrix effects, right, you move that as a sample prep method, but you're then going to need real samples for calibration whose form, be that powder, pellets, as a matrix, is going to match the form you want to run the unknowns in for real calibration. But I did want to caveat that with an or do you, as there are approaches that SciMed are able to support that can possibly get around that. Excuse me. So sort of the second half of mine, before I pass over to Darren, I wanted to just give a bit of a whistle-stop tour through where you would consider different XRF calibration techniques. Now, the most conventional that many people are familiar with a whole variety of analytical tools will be empirical calibration, whereby you have a known set of ideally certified or at least well-characterized reference materials, where you're taking the measured intensity from whatever the method, in this case, the X-ray signal, versus the known assay concentration, and then plotting a regression through that. Whilst may often be seen as a bit of a gold standard for quantitative work, you're still having to get around the need for having a suitable range and diversity of available reference materials that can allow for independent correction of various elemental overlaps and interferences, and have those independent varying ratios of the elements that make up those samples. Otherwise, you can get a beautiful regression, but it's not actually allowing the software to make the appropriate calculations. So what do we do if those suites of reference materials aren't available to us or difficult to attain? Well, that's where fundamental parameters can come in. And if you look at the graphic up on the top right, what that's allowing you to do is the challenge with feeds, soils, and everything else is got a huge amount of organic components in there. And when I give the elemental range for XRF, saying it's spanned from sodium to uranium, it means you can't directly measure those elements lighter than sodium, particularly not with energy dispersive XRF. The reason that matters is it's often a dominant component of the organic matrices of the sample. So using fundamental parameters can allow for modeling of those elemental effects of the matrix without the need to be able to measure and have samples where those unmeasurable elements are characterized. In some circles, this would be described as a standardless approach, which strictly speaking, it is, because you don't immediately need known standards. That has an advantage, but I know in many analytical scientists, it almost becomes a bit of a dirty word to say, if you're running it without standards, it's just a look-see, it's just qualitative. I would argue more that it's semi-quantitative and approaching quantitative with the addition of some matching library reference matrix samples, which is where this becomes increasingly powerful. If we take the FP approach, which is the software modeling the interactions, the unmeasurable components, and how they impact on the measurable elements in order to report a concentration from the inbuilt sensitivity libraries of the device, if you layer on top of that a bit of a training, almost like machine learning, to teach the XRF, here is one or more samples that are akin to the matrix and sample type of those I'm measuring, be that a soil, be that a hay, be that a premix or a final feed, and allow it to say, right, I now got more of an understanding of what the matrix interactions are, and be able to perform a sample family or sample specific bias correction in order to optimize the accuracy versus what would just be spat out by the software as default. And where this becomes really powerful is when this is correlated with ICP results, you're getting very, very close agreement to those sorts of analyses, while simultaneously mitigating the need for all the digestion approaches, which is how you're eliminating those particular sample solid matrix effects in those techniques. To show this, I've just cherry-picked some of the data out of a recent application note by Rigaku. If anyone would like a copy of that, do let me know, because it's available to download as a PDF. But if you look at here, you've got some of the singular nutritional elements and elements that need to be closely monitored, like selenium, for example. With the ICP versus the XRF results here, for those where it was measured by both techniques, you'll see the agreement is actually very, very close. So whilst we're not getting the lowest limits of detection, we are getting very close agreement to more of a standard method. And it's worth noting that even for heavy metal screening, you are getting very close. You can get lower limits of detection of sub ppm. So certainly for that screening approach that I highlighted earlier, for the presence absence of heavy elements, you can get down to detection limits that are approaching those that you need to comply with. But of course, the lower limit detection is not your reporting limit. Your limit of quantification should be at least 3 times that. Hence my earlier slide highlighting around 1 to a couple of single digit ppm would be where I would be confident reporting from XRF. So I think we're doing okay for time, but what I wanted to conclude is, hopefully what I give you a little bit of flavor for there is how XRF could offer a viable alternative for other recognized techniques, giving a lot of advantages in terms of throughput, eliminating a lot of the complex sample prep, being non-destructive, but of course is not without its limitations. And a key one to highlight here in terms of linking into what Darren is going to mention is we're not getting information on things like the proteins, the molecular makeup, speciation of certain elements. XRF is very rigid in knowing I'm looking for these elements and it's total element concentration that I'm reporting. So with that note hanging in the air, I'd like to hand over to Darren to show how NIR can pick up from there and give you more information on the speciation and compounds. Is that fair to say, Darren?
Yeah, thank you very much, Tom.
Brilliant. Thanks, everyone.
Right, let's see if I can seamlessly transition to my slide. Hopefully everything should be showing as it should be.
It looks okay to me at the moment, so hopefully everyone else can see that as well.
Brilliant. Yes, thank you very much, Tom. So moving on from the elemental side of things, I mean, first of all, just a little bit about me. I think there are some people on this call who actually do know me. I've been a product manager at SciMed for 10 years now. Predominantly, my first role was to actually look after the near-infrared spectrometer from VRV. Previously known as GDSU for those people who have been involved with NIR for a long time. I look after the NIR, I look after the handheld Ramens, which is not particularly applicable to this discussion, ideal for warehousing and pharmaceutical, but I also look after power reactors for the north, which again is probably not particularly useful for this discussion. My background is analytical chemistry. I'm a chartered chemist. I did my master's at Huddersfield University, and my background before sales was contract testing, UCAS labs, but also working for spin-outs, supporting the analytical departments for various spin-out companies. So my background is really heavy analytical. Occasionally you might see me out in the hills. So if you need to obviously follow up later, my details there, you're more than welcome to get in touch direct. So the uses of NIR for agri-food and feed. NIR in this industry is quite mature. There are a lot of customers, a lot of companies out there using benchtops. So I've kind of done this a bit more from a handheld point of view, because like anything, things are getting miniaturized, the performance is improving, and there's a keen need to do literally in-field analysis, or at least at line as well. So for those who NIR, you may have come for elemental, but from my side, if you don't know much about NIR, we are looking in the near infrared range. And if you take the electromagnetic spectrum, you've got the visible, you've got the infrared, and we're in the near infrared. So we're very close to the visible range. What are we using the near infrared for? In the very basic form is we're using some form of illumination source. So as Tom talked about using an X-ray tube, we are using just tungsten light bulbs. We are interrogating our sample, and there are various things we can do with that interrogation. We can look at how it transmits through the sample, how it scatters. But what we're really interested in is information that is reflected back. Because in the near infrared range, you get these fingerprints, which are common to different chemical compounds, but you also get some physical information, i.e. you'll get if it's the same chemical compound, but you get a shift in the baseline, that's giving us some physical information that might be useful. And we can use that later on in building calibrations. Whereas Tom was talking about elemental, my background was actually elemental as well, so I'm used to using ICPs and XRFs, but this we're now looking at organic molecules. We're looking at how these organic molecules bend and stretch, and we use that data to hopefully correlate against what is of interest. And the aim is really to do quick measurements in the field to support your businesses in what they do. So some of the applications that we can offer, or some of the applications that people use our systems for, is Lucerne grading, looking at different mazes, silages, looking at speciation. If you're keen to know the species, you can correlate against known species. But also I want to talk a little bit about where people then take it further within the feed industry, looking at raw materials, so actually in a warehouse or in a production environment, and on the back of that is also process monitoring. People wanting to use sensors now, all sorts of processes at various different points, whether it be on goods receipt, right through to releasing of final products as well. So we can look at some other applications that we can support as well. So Lucerne, it's a calculation of the quality of the feed. Various ways to interpret this, but you can look at the prime grade, the first, second, and third grade. So we're using this as a kind of a qualitative tool. Which grade is it? And there are applications that you can download to look at this. And what can also give is qualitative approach. So how much moisture, the ADF, protein, ash, and we can teach the NIR based on the lab results to input that into the model, and you can build your own models based on that to give you the capability to take the lab-based instrument into the field, which is what we all strive to do, to get the most representative sample. You take a sample, you send it back to the laboratory, you wait 2 or 3 days, you get the results. What would be amazing if you can take that device into the field, and this is where we can teach the NIR, the parameters that you wish to predict, and that then obviously enables your customers or you guys to make decisions quicker based on the results that are fit for purpose. Yes, it may not be as accurate as the lab-based method, but as Tom alluded to, if you have to digest samples, clean them up, wait for the results, you need a decision to the nearest percentage now, not to the nearest ppm in 2 weeks. So there is definitely need for these type of devices. What does the device look like? It's a handheld device. It's made by a company that you either know a lot about or know nothing about. VRV is previously known as GDSU. They come from an optical coatings background manufacturer, so it's a company that is absolutely huge, and they make this linear variable filter. Linear variable filter, it's essentially a filter that breaks the light up into its component parts, and that is then glued onto a detector. And one of our claims to fame is, yes, it's out there in space looking for water on various planets. So it's an extremely robust sensor, because it's very difficult to send an engineer to Mars, for example. And inside, again, just to help you understand what's happening, we have 2 tungsten light bulbs, tungsten lamps, which are reflected onto your sample, whatever matrices that is. The light is then reflected onto the detector. So this is the linear variable filter on here. This is the life work of VRV's optics, which is quite crudely said, it's glued onto the detector. Why is that important? You've got long-term stability. There's no need for lasers. There are techniques out there that use lasers from a safety point of view. The lamps are rated for greater than 40,000 hours. And there are no fiber optics. Fiber optics can be quite expensive as well. So it makes it a very robust sensor, ideal for some quite harsh environments. It's handheld, which I mean, it's obviously extremely important when you want to take something out into the field. It's ideal for in-field, at-line, any other portable analysis that you may have. So if you want to go and visit a customer, you're able to scan the samples right at the point of production. What's really important as well is it's got an inbuilt battery, so it lasts longer than the device that you tend to be using, either a mobile phone or a laptop. It has Bluetooth and US connectivity. It is IP rated, and we do provide chemometric software, which can be very expensive if bought from third parties. And one thing I want to talk about is some of the cloud-based solutions, which, like I said, NIR is quite mature in this industry. I think where we can offer is how we can make it more usable for if you have a number of devices, for example, so fleet management. So this video has no sound deliberately, so I can talk over it. So this is kind of showing a real time how it works. So you have a load of calibration that you've either developed or you've been able to get from a third party. You do a darker reference scan. So all this is in real time. It's extremely quick. That's as quick as the calibration needs to be. And then you can select your calibration from the app. Press the multifunctional button, you get the status lights telling you what the spectrometer is doing, and very quickly, within a couple of seconds, you get your results as well. And a lot of work goes into making it that easier. This is where VR have really improved the user experience of analytical devices. They've predominantly been a chemist's tool where you need a chemistry degree to use them. It is designed to be a very easy tool to use. So this is kind of going a little bit off piece, but I think it's very important is we all come from using devices and being able to get the data quickly, whether it be a sat nav on your phone or an app for logging things. And this is very much where the devices are going. Previously, we would have to have a network-based solution if you had multiple devices and to get them all to communicate. Now we are scanning, using the mobile app, talking to the cloud to get the very latest calibration, and it allows your colleagues who are working in a completely different part of the world to be able to log on and look at those results in real time. And the big strive recently is actually being able to do this when the cloud is not available. You have a very powerful phone in your pocket. The calibration is also stored locally on there, so if the internet is not available, you can still predict, where previously that was something that we had to improve on. So that's where the StrataSync comes in. It's a portal for all data. It allows fleet management, which these devices quite often are used by many people within the business. And with that in mind, it has to be ISO accredited for the data management, because obviously nobody wants access to your data, not even us. And the mobile app is iOS, Android supported, and it just allows a very easy user experience. Again, somebody who is not an analytical chemist does not want some of the very complex algorithms that actually are happening in the background but wouldn't be used by the user in the field or upline or in the warehouse, who might not be a chemist, for example. So the mobile app makes it very intuitive on the user. So again, very simple. You log in, you connect to your device, you select the method that you want to use. This one just happens to be carpets because there are people doing carpet recycling out there, and it's a very, very quick way of scanning the material and giving you a pass-fail, a quantitative model, a qualitative model. It can all be tailored to the business needs. One area that I wanted to talk about, because it's very important, is yes, depending on what you guys do, you may have a process after obviously making animal feeds, is using the NIR, in this case a process version of NIR, to allow you to monitor your process within your production, for example. PAT, or process analytical technology, is becoming a very important for real-time results. It allows you to look at large volumes of data, to deploy qualitative and quantitative models, and to give live feedback in a production environment. Which, if you're in a mill or if you're doing any blending, you want to know where your process is at now, not at the end, due to offline analysis, for example. So, for example, this is some durum and soft wheat, and you want to do some quantitative modelling. Here's a very basic video of how this device would be on this sapphire window, for example, and it's continually monitoring based on a time point. So maybe every 5 seconds you're taking a spectra, but in real time you can predict the moisture, the ash, the gluten, and the protein in real time. So you can see how that material is. How it's being processed, and get that data back as soon as possible, which is obviously really important if you need to make a decision on when to stop drying, for example, if you're doing a drying process. So how do these sensors work if you want to do blending? So this is a partnership they have with a company called Matcon, and they make IBC blenders. And what we're able to do in this case is offer a solution whereby the NIR is attached to the lid. Inside the bin goes the materials, and we are scanning every time that bin or the IBC is rotated. And that allows us to compare rotation 1 to rotation number 2, 2 to 3, and see how the blending, or see how the process is changing over time. And then we can action, for example, the blender to stop once it's reached its endpoint based on what the NIR has seen. So based on the calibration, you said I want the endpoint to be when we're in this score plot, and it will send a signal back to the blender. We don't just take one spectrum and compare it to the next. We take a group of rotations and compare it to the next group. So for example, we take spectrum 1 to 5 and we compare that to spectra 2 to 6, 3 to 7, and so on. This allows us to be able to see trends better over time. And then from that, we can decide what we want to plot to look at how that process is changing over time. We might look at the moving block mean, or we might look at the moving block standard deviation and see how that plots over time. What does that mean to the person at line is that you can look at multiple blends and see how they are comparing, and suggest endpoints, for example, for drying, for blending, or maybe on a particular active ingredient. You can look at suggesting an endpoint, and this could be used as a quality tool. Do the batches always perform the same? You can also use it as a production tool to stop the blender. And then you would then you can use NIR to look at different studies. So for example, if you are looking at increasing your blender, you want to go and buy a new one that's much bigger for some of the premixes, you can see how that affects the blending. If you load in a particular sequence, you can see how that affects the blending. Rotation speed, you want to do more blends a day, does that actually affect the endpoint? And fill level as well. Yes, you buy a bin and it may be a cubic meter. Supplier suggests that you fill it up to X%. Can we push that envelope a little bit, and how does it affect quality as well? And then once you've developed your method, just like on the handheld device, you can have real-time deployment as well. Excuse me. So you get real-time process analytics going back to the server to allow anybody to make decisions based on throughput, on what the NIR is seeing. a lot of the materials, well, most of the materials that are in food are a varying input. So by having PAT as a tool, you can cope with varying input to give a fixed output. And that is one of the main reasons why people use PAT technology. So I think that fetches nicely to getting close to the end. So we've now got a time to do some Q&As if anyone's got any questions.
Yeah, thanks, Darren. I'm just monitoring the Q&A, making sure it's functional. It is open. I've just put comments in both the Q&A and the chat for anyone who's trying to use it. If the Q&A is not working for you, feel free to put into the chat. But whilst anyone wants to post any questions, I did have one for you, Darren, actually, that was sent in by someone that couldn't make it, if that's okay with you.
Yep.
The question was about calibration. Let me just make sure I'm reading this correctly. What's the best approach for developing and also maintaining any of the calibrations in one of the handheld NIRs, particularly obviously for feed analysis?
Yeah, so there are some calibrations available from third parties, and they are maintained by the third parties as well.
Right.
And majority of people have come to us for, not in this industry, but many industries, that they want to make their own calibrations, i.e. there are no calibrations out there, or they really want to have their own data within the models. So as mentioned, we give chemometric packages that allow you to build and maintain your own libraries. And periodically you would be referencing them against third-party test houses or any in-house analysis. Moisture, if you have a Carl Fisher or a moisture balance, you can't take that to the field. So the holy grail is be able to correlate against NIR in a controlled environment, i.e. your laboratory, and feed that data into the model. And you know it's your data, it's what's in there is you understand. And that's generally how a lot of models are maintained or achieved.
Okay, great. No, thank you. Oh, hopefully that was sufficient. Actually, there's one that's related to that. It's kind of for both of us, but as we're talking calibration from yourself, what's availability like for any reference materials for NIR for the agri-food? Is that something that's available, or is it more common to develop these sorts of references in-house?
Yeah, there's usually a push to develop these methods. Is one, we have a test house which we use and love, but we want to do more in field. So a lot of reference materials are taken from materials that you characterize, like you said, the XRF, you may have already characterized them against ICP. For plastics, yes, there's a lot of reference materials. For example, I've got a box here that's got a list of known plastic materials, polyethylene, PVC, for example. So yeah.
Yeah, my answer is very similar from answering from the XRF side. Is I think I'd already highlighted that reference materials, there are some reference materials out there for certain standard sorts of feeds and materials, but as formulations develop, they're becoming harder and harder for complex matrices. So it's so much more common for either external lab data or other techniques available in on-site labs to supplement known materials that are akin to the sorts of feeds that are being developed by that particular organization or company, and use that as part of the either full calibration or the matching library sort of tag standards that I highlighted. So yeah, it's getting more frequent that these sorts of secondary references are being developed in-house. We have had a question pop into the chat for yourself, Darren, that says, can you see it?
Yeah, I can see that. So yeah, we're talking about how a peak's identified. For example, you change the moisture content, you'll see a peak at 1400 get bigger and smaller. So there are areas in which in various overtones where you see the peaks for each band, for each parameter. And when you develop a calibration, if you're referring against protein, you'll see the loading on that that part of the spectrum will be quite high, and that's correlated towards protein. So there are some reference peaks that you can use. But for example, when you're doing blending, you actually look at everything because you want to look at the whole spectra. You're not particularly looking from a quantitative point of view that you want to look at one peak. You're looking at the whole spectrum. You're looking at how the whole spectra changes over time. And that's very similar if you're doing speciation as well. You look at the whole spectral range rather than just one particular peak. So it depends on the method where you pick your where you see the biggest loadings for that peak, for example.
And another one from earlier on the other day, sort of related to another different project. I think it's relevant here is, are there any kind of ways that you can integrate, particularly NIR, but also XRF into automation?
So from my side, yes, obviously the PAT is very much akin to automation, i.e. you are speaking to third party sensors or systems. So for example, one of the ways that you can talk from the NIR to a bin blender is via OPC, which is basically saying, send me a tag that says stop when you get to an endpoint. So actually, yeah, from an automation point of view, that's a very mature thing that happens in the pharmaceutical industry. Just like taking a temperature sensor, rather than looking at temperature, we are looking at 128 channels, because that's how many channels I've got in my detector, and you're just making a decision based on an endpoint that you've developed and quantified.
That's great. From my side, automation it's an interesting question actually, because automation is not kind of an off-the-shelf thing offered particularly by Rigaku, though there are now third-party customizations starting to become available for the kind of sample transition and loading, if that's the side of the automation we're talking about in terms of throughput through the instrument. Where I would say something is sort of automation is more in the sample interpretation. That's becoming more common in the software to allow flagged alerts, automated action reports and emails being sent out from things being out of spec. So
yeah,
things like those automated alerts have been around in many softwares for a while, much easier to manage inside the software, more challenging for kind of sample throughput, but yeah, it's not outside the realms of possibility.
I'm definitely seeing the use of AI creeping into NIR now.
Oh, okay.
Yeah, so being able to get the data real time and run it through various AI algorithms and make actions on that, AI is starting to creep in. Definitely seeing that as well.
What about the interpretation of the NIR data? I think you may have already answered. This is a question from me actually, in terms of not being an expert myself in AIs. What are the kind of main barriers or challenges in terms of interpreting NIR data? Is it kind of, if you're not an expert, you can't understand it, or is the fact that
that is always a hurdle. If I go into a new company, I think they understand that NIR can bring a lot to the game, but it's being able to pick those applications which are easily understood by all. Um, yeah, it can be very scary. It is. You're going with an XRF. You have a calibration against a known material. It's much easier to understand that. NIR often for companies that have used NIR for many years, they have a chemometrician, which sounds like a very scary word, but somebody who understands trends in data. The software is always improving to make some of the applications easier. Raw material, for example. Like I said, I can do that on Ramen, on the other device that I sell, and now I can build a calibration just as easy in NIR in the Pro software. So there is a lot of improvements to try and break down that barrier. I always say that you're putting the effort in now, so you can get the quick analysis in the field.
That's the point, isn't it?
Yeah.
It's getting it kind of right then and there, kind of at line in the kind of blending thing you showed. But the field thing is the thing that interested me the most in terms of getting out there and putting it right on the crop, or I think it was a bale of hay or some straw, or whatever it was you're analysing. So,
but that comes from developing the methods in house, which is where it's quite labour intensive. But the payback is I can actually now take it out into the field and do the analysis in the field.
Can you transfer those calibrations onto multiple devices? I mean, is it device specific, or can you kind of port from one to another?
Like anything, if you're going to come to me and buy 100 devices, amazing, that's what we all want. But would you develop it on one device? No. I would always encourage building on multiple devices. But yes, the transferability between devices is excellent. But I always say, if you are going to develop it on multiple, you're going to roll out a lot of devices. Yes, do try and include at least a few devices with different serial numbers on part of the model. It improves robustness. That's all we're trying to do, is make the methods as robust as possible.
Okay, no, that makes sense. I don't want to derail this, because I can see you any other time to ask questions that I might have. Was there any any other final questions anyone wanted to pop in the chat or the Q&A? We're so slightly ahead of time, which is never a bad thing because we're all busy people. I'm sure you're all the same. But as we've got a couple of minutes left, if there are any final questions, please pop them shortly into the chat or the Q&A.
Or if you don't want to pop them out on a forum, because
sure.
I appreciate this. Some people have a bit of confidentiality. If you want to email us, by all means, there's the usual channels. I mean, I'm Darren.nature no, that's my private one, at SciMed.co.uk. And obviously Tom.not as well at SciMed.co.uk.
Yeah, but for all those who are interested and attended, we'll send a follow-up email anyway with a link to where this recording will be hosted if you want to refer back to any of the slides or pictures. Oh, that's very useful.
That's it. And just taking the corporate line as well. We do post a lot of content. We do have a very proactive marketing department, so do have a look on our usual socials, and by all means get in touch, and keep involved.
Yeah, and as I say, if you want to pick the brains of any of the other specialists, primarily around the ICP, as I said, my little shameless plug earlier, we do have a webinar coming up in another couple of months on ICP techniques as well. So thank you to everyone who's made it. And yes, if you'd rather ask any questions, then you can either respond to the follow-up email you'll get or send them to us directly. We'll do the best we can to answer them and see if we can offer any support. But thanks a lot for your time.
Okay, take care. Bye-bye.
Thanks, everyone. Bye-bye.